Hello everyone, welcome back to the second lecture video on the first law of thermodynamics. In this lecture video is going to be a short one, and that is really because we are just going to focus on only one thing, that is what exactly is internal energy. Okay. However, even though this lecture is going to be a short one, it is enough to cover two learning outcomes, which is B and C. So let us move on. Internal energy. We have already had a preview of what exactly internal energy in the previous chapter, where I have mentioned that for ideal gas, it is primarily equals to the Ke due to random motion. And how come we have ignored totally the potential energy aspect of the internal energy? And it is really because under the kinetic theory, the very first assumption for ideal gas is that the intermolecular forces are negligible except during a collision. And that is the key reason why we have totally ignored the potential energy aspect of internal energy. But now we need to understand internal energy more completely. And it is essentially the sum of kinetic energy of the molecules due to their random motion, as well as the potential energy of the molecules due to the intermolecular forces. So that is why now with this definition, you can clearly see that for ideal gas, when we assume that is non-existent intermolecular forces, that is why potential energy will be zero. However, for now, the way that you should understand internal energy will be very similar on how you should understand total energy as well, which is essentially the sum of Ke as well as the potential energy. Okay, but now internal energy, we are really focusing on the total energy at the microscopic and the molecular level. And that is why when we talk about the Ke of the internal energy, we are really just focusing on the random motion of the molecules. The Ke due to the random motion of the molecules, which is dependent on the temperature of the gas, which is something that we have already explained in chapter 11. And then for potential energy, it is really just the potential energy due to the intermolecular forces, which is dependent on the separation of the molecules. Okay, so things like Ke due to non-random motion are totally ignored, and then potential energy due to, like, for example, gravitational potential energy, they are totally ignored because these are the bulk energy. It is not related to the microscopic level. So for internal energy, we are focusing on the microscopic molecular level. So once again, Ke is only due to random motion of the molecules. Potential energy is only due to the intermolecular forces. And these are the aspects where we are interested when we are defining internal energy. And also, for a point that I have already repeated many times, potential due to intermolecular forces are only applicable for the molecules for real gases, or in fact, it is also applicable for solid and liquid. Okay, everything else except for ideal gas, because for ideal gases, intermolecular forces is negligible. Therefore, potential energy due to intermolecular forces must be zero for ideal gas. Now, this is a slide that I have already shown in the previous chapter, but I thought that it is good to reintroduce it here because you have already learned more things and can better understand this slide right now. Recall that in the last part of chapter 11, we have understood that the average Ke is proportional to the temperature of the substance. But if let's say we are talking about the total Ke, then the total Ke should be equivalent to the number of molecules multiplied by the average Ke per molecule. So therefore, two bodies may have the same temperature, but they will have different amount of mass. The one with the larger mass should therefore have a larger number of molecules, and therefore it should also have a larger total Ke, which brings us to the fact that therefore this particular substance should also have a larger internal energy. And this is especially true for ideal gases because for ideal gas, potential energy must be zero because intermolecular forces are negligible. And therefore, the internal energy for the ideal gas is purely the sum of the kinetic energy for all the molecules only. So therefore, in equation form, U is equals to Ke of the molecules. And therefore, it is actually half m average square speed, mean square speed multiplied by the number of molecules, arriving finally with the equation 3 over 2 nkt as well as 3 over 2 nRT. So therefore, we can see from the equation, very obviously, the larger the number of molecule it is, the higher the internal energy, even at constant temperature. Something else to take note is that this equation 3 over 2 nkt as well as 3 over 2 nRT, it only applies for monatomic ideal gas, which is basically the simplest model for ideal gas with only one atoms. In the greater part of the physics, there's other types of ideal gas, like for example, diatomic ideal gas or polyatomic ideal gas. But for the purpose of A level, all we are looking at is just the monatomic ideal gas, so the equation suffice. At the same time, okay, if we are comparing between solid and liquid, okay, it makes things a little bit more complicated. Okay, so for for example, solid, having a greater mass of solid versus a slightly smaller mass of liquid of the same substance, the internal energy is not so straightforward as purely dependent on the number of molecules only. Okay, because for a phase change in state, the potential energy will also change. So therefore, even I may have a smaller mass in liquid form, it may also have a higher internal energy as compared to a higher mass of the same substance in solid form. But if you are feeling confused right now, don't worry too much about it because all these are really just additional information. I'll be happy enough if you can truly understand that the internal energy for ideal gas is purely due to the sum of Ke only, and if you know how to apply this equation correctly in A level. Okay, so once again, we have the internal energy of the ideal gas is purely due to the Ke only, and we have the equation that U is equals to 3 over 2 nKT and 3 over 2 nRT. And for most of the A-level question, most but not all, we are always assuming there's a fixed number of molecules. So for example, the question may refer to you that for a fixed mass of ideal gas, that actually is trying to tell you that they are assuming that the number of molecules is actually a constant. And if that is the case, then my ideal gas internal energy is proportional to the temperature. So in terms of ratio, if I have the same mass of ideal gas at a certain temperature at first, and then some other temperature in the end, then the ratio of the internal energy in the first case and second case will simply be equal to the ratio of the temperature as well. And that also applies for the fact that the change in internal energy will also be proportional to the change in temperature. But do take note that this only applies for ideal gas, because once again, ideal gas, the internal energy is purely equals to the Ke only. And based on the correct physics, my Ke is always proportional to temperature. And that is the only reason why ideal gas internal energy is proportional to the temperature. For real gases, things become different because for real gases, internal energy is equals to Ke as well as potential energy. Only Ke is proportional to temperature. Potential energy is not. And that is why for real gas, okay, it is definitely not proportional to temperature. Okay, the internal energy for real gas is not proportional to temperature. So do take note that this relationship only applies for ideal gas. And internal energy is also uniquely determined by the state of the system. So recall, what do we mean by state? State is essentially defined by the pressure, volume, temperature, as well as the number of molecules. So therefore, if let's say a gas has changed state, meaning the pressure, volume, and temperature has changed, they will also potentially experience a change in internal energy. And to emphasize on things that we have already emphasized before, okay, internal energy is not dependent on the motion or height of the gas container. It is only dependent on the molecules, the gas molecules, nothing to do with the gas container. So therefore, if let's say I have a stationary gas container at ground level, the internal energy of the gas contained in the container should be exactly the same, okay, as another container with the same amount of gas at the same temperature in a flying aeroplane, because the internal energy does not depend on any Ke due to non-random motion. The internal energy does not depend on any potential energy other than the intermolecular forces, due to intermolecular forces. So therefore, like Gpe, due to height, it will not affect the potential energy of the molecules. Okay, so therefore, internal energy is not affected by either the motion of the aeroplane or the motion of the gas container, nor the height of the container. It is purely just dependent on the Ke due to random motions of the gas molecules, as well as the potential energy due to the intermolecular forces of the gas molecules. And for these slides, it is also things that we have already mentioned before. So the term thermal equilibrium simply tells you that the two objects has the same temperature, but they do not tell you that the two objects have the same mass. Okay, so therefore, if let's say there's a different number of molecules, different mass, the internal energy will also differ as well, even if they are actually at thermal equilibrium. So finally, let us compare between ideal gas and real gas. For ideal gas, there's no intermolecular forces, so potential energy due to intermolecular forces must be zero. Whereas that's not the case for real gas, because intermolecular forces is not zero. So for internal energy of a real gas, we need to consider the potential energy. For ideal gas, Ke we have the formula 3 over 2 nKT or 3 over 2 nRT, or using ideal gas equation, we can also convert it to 3 over 2 PV. Okay, but for real gas, we do not actually have the formula for its Ke, But what we do know that whether is it ideal gas or real gas, we do know that the Ke will be proportional to temperature, whether is it ideal or real gas. But for ideal gas, we do have the formula in place here, which we can use to solve for the exact value for Ke. So therefore, internal energy for ideal gas is only due to Ke due to random motion. So internal energy is purely just the Ke. But for real gas, we need to consider the potential energy because intermolecular forces is not zero. And then for ideal gas, since it is the internal energy is only proportional to Ke, and we know that Ke is proportional to temperature, we can therefore conclude that the internal energy for ideal gas is also proportional to temperature. Of course, that is assuming that is a fixed mass of gas, the mass is constant. But for real gas, the internal energy is not proportional to temperature since the potential energy is actually not zero. Then finally, once again, we stress that the bulk Ke due to non-random motion does not affect internal energy. The GPE that is due to height does not affect the internal energy as well. And with that, I'm done with everything that I want to talk about internal energy. We have spent around 11 to 12 minutes just to talk about one page in the lecture notes. We are now left with only one last thing to complete the whole of thermodynamics completely, okay? And that is the...
Morty, tell your parents the first law of thermodynamics.
Did you get any of that?
Sure, Bo,
Understand?
your online source of
Interesting physics lecture.